Thank you, and I want to also start by making a shout out to the people who organized this conference, Pindar Wong and Jeremy. Thank you so much for putting this on short notice. I think it has been extremely helpful, and I hope that the next one in Hong Kong can be as well. So I'm giving a talk on block size here, but we're not going to be talking about any specific proposals, rather talking about the general idea of the block size limit. Why do we have it, and is it even a good thing to have in the first place? So the block size, as you all know, exists as a denial of service limiter. It rate limits the amount of computational resources that a node validating the blockchain can exhaust at any time while validating the block. And the reason why we want to do this is because we are, in the early days of Bitcoin, there was a great concern that by authoring certain kinds of transactions, you could significantly slow down a validator just by broadcasting these or mining a block with some really weird non-standard transaction in it, or just filling it up with tons of spam. And as we've seen in all the talks both today and yesterday, there are a number of ways where if you could increase the validation cost of a node, you could gain an advantage as a miner. And so there's great centralizing pressure that comes from being able to deny service to the network in this way. So there's also, I should say, also a engineering concern here as well. When there was originally no block size limit, it was still the case that you could not create a block more than 32 megabytes because that was the maximum message size. So at some point there has to be some engineering consideration involved in what the maximum block size is, just so that we're able to test software. And there are a few other aggregate limits in the Bitcoin code base for a block. In particular, there's a limit on the number of SIGOPs that can be contained in a script pub key. But these are all derived directly from the maximum block size. So some problems do emerge. In practice, it's observed on typical blocks that the block size does correlate very well with the validation time of the block. But that doesn't always happen when people purposely are messing around with it. You can construct blocks that require lots more time to validate than your typical block, even though you're just coming in under the block size limit. And I'm going to give some examples of actual blocks that are on the blockchain that you can look at and analyze. The core issue here is if we're creating a system that wants to be trustless, that we want to work under a variety of circumstances without any gated access to it, we need to be designing for the worst case scenario. We need to be assured that if miners have an incentive to create slow blocks to validate, that they are not able to generate blocks that are much, 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 much worse than what is typically seen on the network. And so when we say that the block limit is whatever you want it to be, 1 megabyte, 32 megabytes, a gigabyte, you want to be the case that your typical 1 megabyte, 32 megabyte, whatever block is in fact the maximum, has the maximum resource utilization that one can expect. So how bad is it? Let's take a look. There was a block consisting of one transaction other than the Coinbase that was broadcast about a month ago, which was F2Pool doing a wonderful thing for the community and cleaning up a bunch of spam on the blockchain. The only problem is it turns out this block takes 30 seconds to validate even on a beefy computer. And why does this happen? This happens because it is one giant transaction that's about 999 kilobytes, and it contains about 5,500 signature operations. Each of these signature operations serializes the entire 1 megabyte transaction out. It does some work on it first in memory, moving buffers around, serializes it out, and then hashes, resulting in about 1.25 gigabytes of data being serialized and hashed. And the Bitcoin serializer is not fast. That's actually where about 60% of the validation time was, at least on my node. So 30 seconds to validate, and that's on a beefy computer. I don't have numbers on what that is on a Raspberry Pi, but I imagine it is quite long. And most importantly, this is not linear scaling. This is quadratic scaling. So it takes only a 3.2 megabyte block limit to get to 10-minute validation times. And if you're doing 8 megabytes, we're talking 2 hours and 8 minutes. Now, that said, if Gavin is in this room, there's a couple of different ways that he has proposed that this could be fixed, and it actually, such a transaction would be considered non-standard on the network now. So it's pretty much only miners generating it that would be a concern. But it illustrates an underlying issue, which is that some problems we have with transaction size scale quadratically and not linearly. One of the proposed solutions to this is the limit size of a transaction to 100 kilobytes, which is fine until we start talking about, what if we wanted to add CT, confidential transactions, to the Bitcoin mainnet. These require, 100 to a couple, 1 or 2 kilobytes per confidential output. And so it massively increases the size of a transaction, and your average transaction with a couple of inputs and outputs might end up running up against the limit that is put in place. So it's a concern that doesn't really have an exact solution at this point in time if we're measuring things by block size. Additionally, in 2013, Sergio discovered a vulnerability, which was tagged with a number I think is on there, having to do with the max block SIGOPS. This was a limit that was put in place to protect the network. It says that a block can't have more than a certain number of check sigs in its script pub keys. And that number is, I believe, 20,000 within 1 megabyte block. Basically, take the block size, divide by 50. And it's very sensible until you realize that it is not the outputs that are executed in block validation, it's the inputs, and those are completely unmetered. So it is very simple to create. With some lead time, you can create a bunch of transactions that spend, Sergio did some numbers. You can create a single output that does a 200 check sigs. And then it is extremely simple on the attack block to just reference that output, and you automatically add 200 check sigs. And if you do this with a giant transaction, you combine it with the last one, you can create a block that takes an extremely long time to validate. And so Sergio did the numbers. There's a trade-off here in terms of how many SIGOPS you're doing versus how large the transaction you want, because the more SIGOPS you add, the smaller the transaction is, but most of the time is spent doing the serializing and hashing. And he was able to construct one that, in theory, would be about 3 minutes to verify. And those numbers haven't really changed today, since that's mostly hashing, as opposed to database operations. So all of the scalability improvements that we've had didn't really apply. It's probably still take 3 minutes to validate such a block. Now, thankfully, such transactions are non-standard. You can't broadcast. If you broadcast them to the network, they'd probably be ignored. But this is a vulnerability we still have. Finally, we have UTXO set growth being greatly affected by user action. This is a graph of the last 3 months from Satoshi, and it illustrates a couple of different stress tests that have been run in the last couple of days. Last couple of months. And the red line there indicates the point of the first stress test, which grew the UTXO set size from around 650 megabytes up to about 850. So a massive increase at relatively little cost to the people who are running this. And those UTXO outputs, some of them were spent, most of them still on the chain. And for the most part, they're clogging up the database that is used by Bitcoin to validate blocks. So they're making every block afterward slower. So how bad is it? It's pretty darn bad. If you're trying to engineer a block to validate as slowly as possible, you can get it by these past numbers I just showed you to be somewhere between 10 and 100 times slower than a typical block. So your average 1 megabyte block, you may make an argument that our Bitcoin nodes are able to support it just fine. But if you're looking at the worst case, you take what your node can do for a 1 megabyte block, takes a couple seconds to validate, or hopefully less than a second on a fast computer, multiply that by 50 to 100, and that's what you should be engineering for if you're using the block size limit, if you're using block size as your limiter. Furthermore, these attacks are relatively cheap, as we've seen with the stress tests that have gone on. If it was one stress test, maybe I would think it was a fluke, but so far there have been, I think, 3, and they don't seem to be stopping. And in each one of these cases, we see this quadratic scaling due to the size of the transactions. And again, these are not theoretical; they're observed in the wild. So the question is, if we're thinking about proposals for scaling Bitcoin, why then are we using the block size as a measure for resource utilization? Why are we talking about raising the block size? Perhaps we should be thinking about using something other than block size, using a more direct measurement of the resource consumption of a block. So what affects full validation? Well, block size is still on that list, and the reason why it's on that list is worst case latency for transmission. We've had a couple talks here about various network coding schemes like IBLT. These have the capacity, or in the Bitcoin Relay Network, which has the capacity to fit a block within a single TCP packet, minimizing latency effects no matter the block size, sort of. That's a good thing, but that's assuming minor cooperation. So with IBLT or related schemes, you can create a block of just about any size, and as long as you create it in such a way that you're using transactions the network knows about, you can get your latency down. However, if you're thinking adversarially and you want to maximize the amount of propagation delay for your blocks because it gives you some advantage, then it is trivially simple to create spam that was unbroadcast before your block was found and include that. So the maximum block size does in fact impact full validation. But we have other factors here as well that we're concerned about. I had shown that UTXO set size. Patrick had given a talk earlier about the time to do initial block download. There's a related calculation you can do, which is if we don't want to grow the UTXO size by more than a certain amount per year, how large of a block do we want to support, given some assumptions about how much UTXO is created versus spent in a given block. And when we're looking at script, we have the SIGOP limits. There's also a couple of other operations in the script language which are not constant time. For example, duplication. You can create some large. You can create large items on the stack and then duplicate them many times. There are ways that this can be protected against, such as preventing opdupe from creating super large, creating too large of an item on the stack, and just rejecting the transaction. But it does exist there as a memory usage. So if you want to drive up, like one transaction uses a couple megabytes of memory or something like that, it's fairly doable. The libscript, which is our library that handles the Bitcoin script execution engine, does not at this time track a lot of information about which opcodes are being used and how many of them, how much how much memory space was required, but this could be done. And so it'd be a little slight refactoring to get a little bit more insight into what resource usage is made by libscript, and even perhaps to get rid of memory allocation in there entirely, and it just, you tell it, okay, this script is going to take 1.5 megabytes. Here's a chunk of 1.5 megabytes that you use to validate. But those are some refactoring changes we could make, and so then we could have as a input into this metric, whatever it is, the opcode count executed and space requirements and such. Elliptic curve operations, these are check sigs. These are relatively expensive to run on a CPU. They're usually not hardware accelerated. Right now we are measuring those in outputs, which is, as I said, stupid. There's no reason we should be doing that. We should be measuring inputs, and so that's a change that we can make. Finally, when we saw with the F2 pool thing block, we have this issue of our blocks being slowed down by the amount of data that is being hashed. So if we just checked or aggregated and accumulated how many bytes were hashed in every step along the way in validating a block, and then use that as a limit, that would also help prevent things like the F2 pool block. So that's a lot of different parameters in there, and there's an infinite variety of functions that you could use to combine these together into a single metric. But the reality, and I would encourage anyone who wants to look at it to consider different functions. There might be a better one. But the reality is that for a lot of engineering reasons, a linear combination makes sense. So just linear function with coefficients on each of those parameters, summing up to some number that you use as a metric instead. And the reasons for this are fairly mundane. It's simply that the existing system right now is a linear function of one parameter, block size. And so it's pretty much a drop-in replacement to have a much more complicated but still linear function. It also has the nice advantage that your coin selection algorithm remains a simple knapsack algorithm, not a multidimensional one, which does not have straightforward solutions. So a linear combination of factors would be a drop-in replacement that you could use in pretty much any wallet software. But some of these coefficients are not like the others. So if you're thinking about, okay, how many single opcode executions are equal to 1 round of SHA-256 or something like that. You can just measure that and figure it out and decide fairly well, because you're comparing CPU running time. But how many bytes of RAM equals 100 milliseconds of CPU utilization? Well, that's a little bit more variable, and in fact it changes over time as computer hardware evolves at different speeds. And some of them are kind of intangible. For example, we are kind of not, it's kind of arbitrary how you compare growth of the UTXO set size to how costly it was to validate a transaction. So there's a little bit of room for future work there in figuring out exactly how that should be combined together.
Mark?
And I'm about done. So there's a summary that I pretty much said, and I want to thank you all. There's going to be an extension of this work presented at the Hong Kong workshop if it's approved by the committee. So I hope to see you all there, and thank you so much.
Thank you.